Thank you also very much for the invitation. Okay, today I'm going to talk about a new, for me, topic. It's signatures of chaos in non-integrable models of quantum field theory. It's a joint work with Micha Srdinsek and Tomas Prosen. Micha, maybe, I think I saw him in the audience.
Yes, I'm here.
Great to see you. So this is a work that was published in PRL at the beginning of the year. This is the link if you are interested in checking out the paper. As a brief summary of our findings, let me start with a general slide about what is integrable and what is non-integrable, and how do we distinguish quantum many-body systems based on characteristics of their spectral statistics. This, of course, everybody knows. Integrable models exhibit level crossings, while non-integrable models exhibit level repulsion. Here is a nice figure that I got from Micha's master thesis, which shows how the level dynamics somehow change when we change the parameter lambda in a Hamiltonian that describes our physical system. So if H0 is an integrable model, then we have level crossings, and as we increase the parameter lambda, you start seeing that crossings are more and more prevented gradually, and you see more level repulsion for larger values of lambda. This is a topic. This is an analysis of in the past single or few body problems described by finite dimensional Hamiltonians usually. But very recently, well, I would say in the last couple of or more decades, it has become a very popular topic also in many-body physics. So this is a plot of from a paper, a review paper by D'Alessio, Caffrey, Polkovnikov, and Gold, which shows the transition from Poisson statistics for integrable models to GOE statistics, randometric theory ensemble for a non-integrable model, which is a spin chain, so a many-body system this time. Okay, so yeah, the distinction between integrable and non-integrable models is that the distribution of level spacing is markedly different in the two cases. The Poisson distribution has the characteristic that its value at 0 is non-vanishing, while in any randometric theory ensemble, like the Gaussian orthogonal ensemble that we are going to focus on here, its value is 0, exactly because levels repulse, so there are no crossings. And we wanted to check that in a set of models that describe 1+1 dimensional quantum field theories. So for those who haven't who don't know what these models are, the names may sound familiar to you, like the double sine-Gordon model, the massive sine-Gordon model, and the 5-fourth model. These are nothing but one-dimensional, in this case, models, bosonic field theories that are continuous. So there is no lattice here. And relativistic. So these are models that come up when one studies interacting models of elementary particles, like in high energy physics. And perhaps the 5-fourth model is the one that most of you might have heard in courses on relativistic field theory. The sine-Gordon model is a model that is interacting and has interesting topological properties. And the double sine-Gordon, massive sine-Gordon models are generalizations of the sine-Gordon model that I'm going to keep more details about. All of these are continuous bosonic field theories that are also relativistically invariant. And we know that there is a lot of interest in this topic in the last years, using new techniques, new theoretical techniques. But here we wanted to stay more traditional and check the signatures in energy level spacing statistics and eigenvector component statistics. So based on quantum chaos predictions, we would expect that energy level spacings for these non-integrable models, all of these three models are non-integrable, should be GOE-like. And indeed, this is what we see in this plot on the top. So we see that by changing the parameters, I'm going to explain in detail later, we can see that the crossover from Poisson distribution of level spacing statistics to GOE-like, so from blue to the red curve. But when we check for the same models, the eigenvector component statistics, we see that these exhibit a quite exotic behavior and quite unexpected, in that even when we are at the non-integrable point, so the red point in parameter space, the distribution is strongly non-Gaussian. So we would expect that if these models satisfy the predictions of quantum chaos, we would see a Gaussian distribution of eigenvector components, but instead we see these long tail distributions, which, if you check the log-log plot, looks like they are algebraic decaying tails. The method that we used is the so-called Hamiltonian Truncation method. This might also be unfamiliar to most of you, so I'm going to talk about this in detail in my talk. So before I continue, let me give
Can I ask something?
Yes.
Before you sort of get deeper into this. So, I mean, I assume you're going to explain how you go from, you give me a field theory to me putting something on a computer and finding eigenvectors. I mean, I guess you're going to explain this, right? Because to me, it's not obvious, which might be because I'm not an expert. But
yeah, this is actually a significant part. This is probably more technical aspect, but I did spend quite a few slides to explain this. Because as you will see, even just the fact that the Hilbert space dimension is infinite, traditional numerical methods like simple exact diagonalization is not going to work here. So we have to do something different. So I'm going to give a detailed explanation of what this numerical method that we use is. But before that, I will give a description of the models that we studied: the double sine-Gordon, massive sine-Gordon, and 5-hot model. Then I will talk about the numerical methods of Hamiltonian truncation and a little bit about the measures, even though this should be familiar to most of you. As I said, we focused on level spacings and eigenvector component statistics. And then I will pass to the main part of the talk, where I will present the results of our analysis. Okay, so let's start with the models. These are the three models that we studied. They are described by these Hamiltonians, written in this concise form. H naught is a bosonic field theory that describes essentially the oscillations of a string. If I find the Heisenberg equations of motion for this field theory, this is nothing but the wave equation. Pi is the canonical conjugate field of phi. These are bosonic fields, they satisfy canonical commutation relations. So this is nothing but the Hamiltonian of a classical string, which is now quantized. If I put periodic or Dirichlet boundary conditions, if I attach the string at the edges, then I get nothing but the normal modes, which are harmonic oscillators, and I have an infinite number of them, starting from the wave number 1 pi over L essentially, and then integer multiples of this fundamental frequency. So I get an infinite tower of bosonic harmonic modes, each of which is described by an infinite Fock space, obviously, because it's a bosonic mode. And now this is obviously a free Hamiltonian. It's quadratic in terms of the fundamental fields. And now I perturb it, adding interactions to the Hamiltonian. And we have these different types of perturbations that we considered. V beta is an interaction of the cosine type. And the double sine-Gordon model is described by adding two different frequencies, two different terms of cosine type with different frequencies, beta 1 and beta 2. The massive sine-Gordon model is described by Hamiltonian, where the first perturbation is of the cosine type, and the second perturbation is of a quadratic type. This is called the mass term in field theory, where this is not an interacting term, but it's just a phi square term. And lastly, the phi-fourth model is described by a mass term and an interacting term of the form phi to the fourth. So whenever we have a polynomial of order higher than 2, this describes an interaction. All of these models are non-integrable. If we set lambda 2 equals to 0 or lambda 1 is equal to 0 in the double sine-Gordon, we get the sine-Gordon model because we have a single frequency instead of 2. And that model is integrable. So we have an interesting way to check the change of behavior from integrable point to a non-integrable. So it's probably hard to get an intuition about the physical behavior of these three models. And for this reason, I prefer to start with the sine-Gordon model, for which we know much more about. So this is described by this Hamiltonian written explicitly down. You see that the interaction corresponds to this cosine potential, and because of the fact that the cosine is a periodic function, so it has infinite minima all at the same energy level, we have an infinite set of degenerate vacua ground states. And we can have transitions, we can have a crossover from one vacuum to the other, which corresponds in the classical case to a soliton. It's a king where the field starts from 0 and goes to 2 pi or an integer multiple of 2 pi. And the classical case, it turns out that these solitons, these king configurations or solitons, are stable, so they scatter elastically, and they can also form bound states. Which means that because of the fact that their scattering is elastic, their number is preserved, and the field theory is integrable. So it has all the nice properties that we know about integrable models. Now, in the quantum case, it turns out that the same structure is preserved. So we can describe the system in terms of solitons and multi-soliton bound states, the breathers. And the scattering between many particles, many solitons can be decomposed into a sequence of two-particle scattering processes, which is the characteristic property of integrability. So we have all the nice properties that we know.
Question?
Yes.
Is phi a complex field, or is phi complex or real? Is that
phi is a Hermitian field. It's
okay, and
it's compactified. In this case, in the sine-Gordon model, it's compactified so that beta phi. I mean, the radius. It's a field that takes values on a circle with a circumference 2 pi over beta, which makes the cosine makes it match with the cosine. This is not a necessary thing, of course. We can choose phi to be a different field, and in fact, in the double sine-Gordon model, we have two frequencies, so the field is not really compactified according to one of them. Before I move on, let me say that the sine-Gordon model has also some other interesting properties. It has an interesting phase diagram. It exhibits a Causalis-Thales phase transition. It's this black line here, where this is the interaction. This is the mass parameter m, The interaction delta is a reparametrization of beta, which is conveniently chosen so that the KT phase transition starts at point 1. At point 0.5, the model becomes equivalent to a free Dirac fermionic field theory. And it is also a model that is known for the duality with the massive Thirring model. So the massive Thirring model is in general an interacting model of massive fermions. But when we choose the parameter delta to be at this specific value, then it becomes free. And the boson fermion duality is one of the first dualities that were discovered in field theory, given in explicit form by Mandelstam in 1975, who gave an expression for the fermionic degrees of freedom in terms of the bosonic variables that I introduced before. These fermions are nothing but the solitons at the point at the Thirring line where the model becomes free. Okay, that's about the physics of this model. I should also say that the sine-Gordon model has been quantum simulated. That is, it has been implemented experimentally in an analog quantum simulator system, which is in practice a ultra cold atom system that is controlled by an atom chip. This was done in the group of Schmid-Meyer in Vienna. And there is a nice set of experiments that they have done, like they have achieved the observation of a generalized Gibbs ensemble, and they have also seen the non-trivial behavior that emerges from the presence of solitons in the system. Here, for example, I don't want to go into the details, but here you can see some interference patterns that demonstrate the presence of solitonic excitations in the system. And these full distribution functions of the phase field phi show that at integer multiples of 2 pi, we get some peaks that are characteristics of the presence of solitons. So there are experiments that can study the dynamics and the equilibrium properties of the sine-Gordon model. Now, the double sine-Gordon model, perhaps less intuitive or less understood from the physical point of view, is described by perturbation of the sine-Gordon model by an additional cosine term with a different frequency. And now the field topology becomes non-trivial. The solitonic excitations of the sine-Gordon are no longer stable, and they decompose into other particles. So the double sine-Gordon model is non-integrable. I should have added another slide to talk a little bit about the massive sine-Gordon model. My main focus is going to be on the double sine-Gordon model, but another generalization of the sine-Gordon model is when we add a mass term, as I said. It's this type of term here, which is also interesting because it can be mapped using the same boson-fermion duality to the Swinger model, which is the one-dimensional version of QED. So these models are, they have some interesting topological properties, but at the same time, they bring us one step closer to describing real high-energy systems like gauge theories and so on. Even though we are still talking about one-dimensional systems. Okay, that's about the models. Let's go now into the method, description of the method that we used. As I said, the problem in systems with an infinite Hilbert space, infinite dimensional Hilbert space, is that exact diagonalization techniques are not possible, of course, and one should resort to some sort of approximate numerics. One approach that has been introduced by Zamolodchikov at the end of 70s is the so-called truncated conformal space approach, which is the method that we used. And it's one version of the more general set of Hamiltonian truncation methods, which are suitable for the study of 1+1 dimensional quantum field theories, independently of whether they are integrable or non-integrable. And it's based on ideas from the normalization group theory and conformal field theory. This is the early version of normalization group theory. So we are talking about perturbing a conformal field theory by a relevant operator, which is the main idea behind this approach. And here we are using the algebraic tools of conformal field theory to both construct the basis for the diagonalization and to compute the matrix elements of the interaction of the perturbation of the conformal field theory. And if we do a perturbation using a relevant perturbation, delta H, I should have said that this is relevant, sorry for the typo, then we can expect, based on RT theory, that the numerical spectra will converge as we increase the size of the truncated basis. This is just some general information about the method. I'm going to give some more practical information later on. I would just like to say for now that the reason why we choose this method is because it works for continuous field theories, unlike standard tensor network based methods which work on lattice models. Of course, there is a continuous MPS approach which applies to continuous theories, but so far it hasn't been applied extensively to the models that we are interested in here. It has been used for the study of the sine-Gordon model in one paper, as far as I know, but not extensively, and apparently there is not much flexibility to study the things that we are interested in here. It has been used not only in 1+1 dimensional models, but also recently in 2+1 dimensional models by the group of Ritschkoff. I can give more details on these references if you are interested in. And it can capture non-perturbative effects. And recently also out of equilibrium properties of these models, as I will show in a few slides. Now, these are the positive, the advantages of using this method, but there are also strong disadvantages, and the most important of them is that it doesn't address the problem of the curse of dimensionality. So what we are talking about here is not a more elaborate version of RG theory like in tensor network-based techniques, but a simple exact diagonalization technique in which the size of the truncated basis is increased, and one checks the convergence of the results. So it has not so far implemented in a way that it can result in an efficient way to calculate the properties of these models, despite the fact that the Hilbert space dimension increases exponentially with the number of degrees of freedom. Okay, more details about the methods. Our objective is to find the low energy spectrum of a quantum field theory in finite volume. This is described by Hamiltonian H, which now we write as a sum of a solvable part H naught and the perturbation delta H. And then, since the H naught part is solvable, we can find all the eigenstates, at least in implicit form, all the eigenstates and eigenvalues of the Hamiltonian H naught. And also we can use the algebraic properties of the model, at least this is the case for conformal field theories, to calculate matrix elements of delta H in the truncated eigenbasis of H naught. So we write a finite dimensional version of delta H in a finite truncated basis of H naught. And what we do then is to simply diagonalize this finite matrix in this subspace. Then, of course, this is, if we do that for a general model, this is not going to give us any meaningful spectrum. Any spectrum that would be close to the physical one, to the real spectrum of the model, because it's infinite dimensional. But if we do it for in the case where H0 is a conformal field theory and delta H is a relevant perturbation, then RG theory tells us that the perturbation is going to modify the low energy part of the spectrum of H0, but not the high energy part. At least this is the intuition that we have from the early days of RG theory, right? So this tells us that if I take a truncated version, truncated form of the perturbation and increase the cutoff, and as we expect, the number of states in the truncated basis increases very quickly with the truncation cutoff, then we are going to get numerical spectra that change every time we change the cutoff, and we repeat the diagonalization procedure. But at higher energies, they are going to be closer and closer to those of the unperturbed model, exactly because relevant operators have the property that they modify the low energy part, they open a gap in the Hamiltonian and so on, but not the high energy part. So
can I ask something?
Yes.
So if it was irrelevant, what would actually be the situation here? Suppose I took an irrelevant perturbation and tried doing what you said, what would I see?
So if the perturbation is irrelevant, then the opposite is going to happen. The high energy part is going to be modified. The low energy part is not going to be modified significantly. So every time we increase the cutoff, we are going to get a completely different spectrum. It's going to flow. It's not going to converge. It's going to change into something different. And therefore, we are not going to get any closer to the real spectrum. This has still been used to get information about irrelevant perturbations. I can give more details later. This is a bit out of the scope, but definitely it's not going to give us numerically correct spectra or close to the correct spectra of the Hamiltonians that involve irrelevant perturbations. So the goal is even more generally than this conformal space approach that we are using here. The goal of the Hamiltonian truncation method is to find first the model that describes the high energy part of the perturbed Hamiltonian, and find a model that is integrable, exactly solvable, and describes this high energy part. And then the rest of the Hamiltonian is going to be considered is simply the perturbation in this framework. And exactly because the perturbation has less effect in higher energy scales, by increasing the truncation cutoff, we can expect that the numerically derived spectra are going to converge to the right ones. I should emphasize here, I didn't say it explicitly, that the truncation in this method is done so that we keep the low energy part of the unperturbed Hamiltonian. So we keep all states that have energy below some truncation cutoff E cut, and then we increase this cutoff and we see how the numerical spectra change. Okay, so this method has been used something like 30 years ago to diagonalize the sine-Gordon model, and the numerical results agree very well with the theoretical predictions based on integrability. But more recently, there are applications that have been used to calculate the entanglement, a sort of entanglement. It's called left-right entanglement or chiral entanglement in perturbed conformal field theories in 2019. It has been also used in the sine-Gordon model to describe thermal equilibrium properties and quench dynamics. So here we were, in this publication, we were able to give an explanation of the experimental results for the non-Gaussianity of thermal equilibrium states as a function of the temperature. And we also got some interesting results for the oscillations after a quantum quench. It has been used also to study oscillations in phase space. These are all experiments that have been done already in cold atoms, and there is no theory to describe these models, these experimental results in the quantum regime. So far, the experimentalists have to resort to classical field theory methods in order to get some intuition about what is going to happen in the experimental system. We have also used it to calculate the spreading of correlations after quants, and there we see really exotic effects that we didn't expect, like oscillations in the background value of the correlations. It has been used recently by Kukulian to calculate the dynamics of the Swinger model that I mentioned briefly earlier, which is nothing but the 1+1 dimensional version of QED. So it was possible to verify the energy spectrum and compare it to predictions from lattice discretizations, and also to study the same question about spreading of correlations after quantum quants. So there is a number of interesting applications recently and some activity. Now, what hadn't been done in the past is to study level spacing statistics. Actually, there is one paper by Koenig and Giuseppe Musardo that did this something like 10 years ago, I think, but in completely different models, and verified the emergence of chaotic level spacing statistics, which is something that we also re-verify in our work. But instead of the fermionic model that they considered there, we are studying here the double sine-Gordon model, so a different model. Okay, the measures that we are interested in are a convenient measure to study level spacing statistics is to calculate the distribution of consecutive level spacing ratios, Rn, which is defined like this. So we calculate first the difference between energy levels. Then we take the ratios of the differences of two consecutive pairs of energy levels. This is Rn. And then we find the distribution of these values of R. This is convenient because in this way, the results are not dependent on the spectral density, on the density of energy levels, which usually requires the unfolding procedure before the analysis of the statistics. Instead, here we just have to calculate this quantity, plot the histogram, and check how it compares with those of integrable models and those of GOE models, of the GOE model. So in the Poisson case, the distribution is like this. In the GOE case, it's like this. So we see that there is, again, the characteristic property that P of R vanishes at small values of R. And if we want to have a single number that is an indicator of whether we are in the chaotic or in the integrable regime, we can simply calculate the mean value of this quantity R tilde, which is the minimum of R and 1 over R, which was proposed by Hughes and Oganessian in 2007 as a simple indicator of integrable to chaotic behavior. So in the integrable case, this quantity takes a value that is close to 0.386. In the GOE case, it's close to 0.536. Okay, so yes, yeah. And the other measure that we are interested in is the eigenvector component statistics. And for this one, if I take a matrix out of a Gaussian orthogonal ensemble and diagonalize it and find the eigenvectors, then I will find that the components have a Gaussian distribution, which means that the norm squared values of the eigenvector components follow the so-called Porter-Thomas distribution. And it's interesting that this, even these days, there are studies of nuclei, and which is how this distribution was first proposed in 1956. and so that the nuclei are described, the resonances of nuclei are described by this distribution. Okay, so now for us, the reason why this is important, I mean, the validity of whether the Porter-Thoma distribution describes the eigenvector component statistics in a real system is important because it's closely related to the Eigenstate Thermalisation Hypothesis. So it's closely linked to whether thermalization is going to happen in the specific model. I can again explain this in more detail. The reason is that the off-diagonal components of the matrix elements of a local observable are assumed to be random, to be Gaussian, and this is what happens if the eigenvectors themselves are Gaussian. And if this does not happen, then it would be really, really difficult to see thermal behavior. So it has been taking the distribution of eigenvector components is an easy way to check, for example, for quantum scars that you know very well about, and so on. There are recent works that use the eigenvector components to distinguish scar states from standard ergodic states. Okay, so let's now pass to our results. As I said, I'm going to focus on the double sine-Gordon model, which is described by this Hamiltonian. And let's start with the level spacing statistics. As I showed earlier, the distribution of R values, which I defined explicitly now, is given by these plots for two values of the parameters beta 1 and beta 2. So when beta 1 and beta 2 are equal, the difference is 0, then what I get is the simple sine-Gordon model. There are no two frequencies, but just one. So the model is integrable, and that's why the distribution follows the Poisson curve. When beta 1 minus beta 2 increases, I go further and further away from the sine-Gordon line, and then the distribution becomes comparable to the GOE distribution for the R values. And as I said, the mean value of R tilde is a single value that can indicate whether we are in the chaotic or the integrable regime, and we see that it starts perfectly close to the point 0.386 and goes close, but still below the value 0.50 something, 53, if I remember correctly. That corresponds to the GOE statistics. Now, if we want to see how these values, how this R tilde indicator changes when we vary the parameters beta 1 and beta 2, we get this sort of phase diagram, if you want, where the blue values correspond to Poisson statistics and the dark red values correspond to chaotic statistics. So whenever beta 1 is 0 or beta 2 is 0 or beta 1 is equal to beta 2, what we get is the sine-Gordon model, which is integrable. When we are away from these three lines, the diagonal and the horizontal and vertical lines, we get a red value, which is characteristic of the of chaotic behavior. So the phase diagram has the behavior that we expect. Now, if we vary instead the parameters lambda 1 and lambda 2, which are parameterizations of these masses mu1 and mu2, so these are essentially the strengths of the perturbation, then again we get the behavior that we expect, that when one of them is equal to 0, then we have the sine-Gordon that is integrable behavior, blue colors. When we are at intermediate values of the mixing ratio x, we get dark red values. And if we want to see a normal list plot instead of a density plot, this is on the right side. So you can see that at a point 0.5, when the two terms are of equal strength, we are at the maximum value of our theta mean, which is very, very close to the chaotic value. Now, what's also
Can I ask something about the previous slide?
Yes.
So on the one on the right, so I guess this x is, yeah. So x is the, okay. So you're
X
saying
is
that
the
when,
mixing parameter.
yeah, you define it underneath. So you're saying that if they're equal, I get the maximum, which is the 0.52, whatever that you get for, but for that, for let's say x is 0.1, I get some intermediate value of r. I mean,
Yes.
is it that, I mean, or rather, do you know whether I get this because so is it like a finite size effect in the sense that if I looked at the bigger system, I would actually get 0.52, or is it really some intermediate type of statistics, and that your model is somewhere in between? Like, the model, if I look at it as an random matrix, is sort of intermediate. So, or is it difficult to tell?
So this is rather hard to say. Well, I should first say that, as the title says, and I didn't actually highlight, we see this behavior already in the perturbative regime, and that was surprising actually, because in few body quantum mechanical systems, we expect that it's only when we are sufficiently far from the integrable point that we get chaotic behavior, right?
Can you define perturbative actually here?
So perturbative here means that this will be clarified later on, because I need to give some information about the unperturbed model. But just briefly, the unperturbed model has an extensive degeneracy, level degeneracy. So there are huge energy cells which increase exponentially with the energy, their size, I mean, which all have the same energies, and therefore, when I switch on a perturbation, I should apply, if you want, degenerate perturbation theory, if I want to calculate the first order effect of the perturbation. And you should recall here that what happens when we switch on the perturbation in a degenerate model is that all the energy levels that are in the same energy cell, they get mixed with each other immediately when we switch on the interaction, but not with those of the other cells, because those are at finite energy distance far away. So the in-cell eigenvectors become immediately close to, I mean, the properties of the perturbed in-cell eigenspace becomes immediately chaotic as long as the level spacing statistics are concerned. Actually, this plot that I'm showing here is exactly the limit lambda, lambda 1 and lambda 2 go to 0, but in this specific direction. So exactly at this point, the corner of this diagram, we get this type of statistic. So it's exactly the direction of lambda 1 over lambda 2 that determines whether we are going to end up in the integrable or the non-integrable regime model.
Maybe let me ask a last question then on.
Yes.
Well, actually, no, maybe continue and I'll ask you at the end.
Okay.
Actually, sorry, I have a question. These results are all for the thermodynamic limit already, right? There is no system size. Is that correct?
No. I mean, the starting point of the method is to focus on a finite size system.
Okay. What's the size dependence of this? So it could be that the integrable point, whether you get this in the perturbative regime already, maybe this depends on the size.
So that's another piece of information I should give. The lambda parameters scale with the system size. So when we increase the system size, lambda also increases with L. And therefore, the perturbative regime refers to a small system. And when we increase L, we go further and further away from the perturbative regime. Now, the problem with the Hamiltonian truncation method is that convergence is only guaranteed in a small corner of parameter space. And in particular here, when we increase lambda, and we go far beyond the perturbative regime, then the convergence is lost. So we cannot rely on data for large values of lambda or equivalency L. So we cannot describe the thermodynamic limit here. Right, so I hope this makes it clear. In this plot, I'm showing more explicitly what's happening when we increase the parameters lambda, which are encoded in this differently named parameter L here. So when L increases, and this L controls both the lambda 1 and lambda 2 that I showed before, then we start from, for small values of L, we are in the perturbative regime, and the eigenvector matrix, so just the eigenvectors one after the other, has this very particular form that can be explained exactly by degenerate perturbation theory, as I explained earlier. While when we increase L, which means we increase the interaction of both lambda 1 and lambda 2, or in other words, that we increase the system size, then we go far from the perturbative regime, and the convergence of the method becomes worse. So we have really good convergence for L up to the order of L is equal to 2, but then convergence gets lost. And we have very stringent tests of convergence, which I'm going to talk about later if there's time. So
actually, can you define convergence here?
Yes, right. So it's quite difficult, right? First of all, because the density of the levels is very high. So there are crossings. Every time we increase the cutoff, we get a different value, a different approximation for the same energy level. And because of the fact that the levels are very dense, it's hard to even track which level is what and how its value changes by increasing the cutoff.
No, but what I'm asking is simpler. I mean, how would so here you're showing some matrices, right? And you're saying the ones on the left for lambda is small are better converged. But what does converged literally? What does it mean? Do you mean that it stops changing as the upper limit gets increased?
By convergence, I mean that the spectrum doesn't change when we increase the cutoff. So we're talking about convergence with the cutoff. Here, what I showed is how this matrix change when we increase L. But not all of these data are equally reliable for all the different values of the parameters. So for very small values of the interaction, which is encoded this, which corresponds to this L going to 0, we have very, very good convergence, meaning that both the energy eigenvalues and the energy eigenvectors, the low energy, at least part of the spectrum, doesn't change as we increase the cutoff. While when we move to larger values of L, or when we move to larger values of beta of the interaction parameters, all of these parameters affect the convergence of the method and whether the data are reliable or not. So here we had to deal with the question: how do we decide if the data that we get from out of this method are reliable, are close to the actual spectra or not? And this is a question that I can give more details later. But to get an idea, we show here how the parameter, the quantity R tilde mean changes at the two different points in parameter space that I showed before when we increase the parameter L. And you see that for small values of the parameter L, all these curves are on top of each other, here, for example. And these different curves correspond to different values of the cutoff. So for values of the order of L is equal to up to 1, I would say, the curves are sufficiently close to each other, and we can talk about convergence of this measure. But when we increase further L, then the different curves start deviating from each other, which means that we have strong fluctuations, which are numerical errors, and we cannot rely anymore on these data. But up to L is equal to 1, or I would say L is equal to 2, we can, or 1.5, the curves remain rather stable. I have to say from the beginning that the convergence is very slow in this Hamiltonian truncation method. So it decreases algebraically with a cutoff, while the size of the truncated space increases exponentially. So by increasing by 1 the energy and including 1 extra energy cell of the unperturbed model, we include exponentially many states, but we don't improve the results too much. So we have to really work with matrices of the size of 85,000 states. And still, we could only get reliable data for the lowest 3,000 up to 3,000 or 5,000 states of the energy spectrum. So something like 5%, I would say, of the truncated space size. Okay, so yeah, focusing on these 2 points, we checked what happens for the level spacings and at the same time for the distribution of eigenvector components, because we wanted to see what happens in different energy windows and whether this very special form of the Hamiltonians, which has this shell structure, affects the distribution of eigenvector components. But we found that even when we are we throw away all energy, all eigenvectors, but those in a single cell. So when we focus on a single cell, we still find that the distribution is strongly non-Gaussian. It has the algebraic tails that we saw before, or at best you could say that they might be close to exponential, but nothing really close to Gaussians. So we see strong deviation from what we expected from quantum chaotic prediction. And at the same time, we said maybe this is a peculiarity of the methods, of the fact that we are perturbing a conformal field theory. So let's see what happens in the 5/4 model, where the Hamiltonian truncation method works in a slightly different way, and instead of perturbing the conformal Hamiltonian, we are perturbing instead the massive part of the Hamiltonian. So we take the Klein-Gordon Hamiltonian, which is H0 plus the mass term, which is still integrable and still easy to diagonalize and to calculate the exact eigenvectors. And then we perturb it with a 5/4 term. This has been done extensively by the group, Ritzkov's group in Paris, and people in the high energy community. And we find that even though the method is different here, the truncated basis is not conformal, and it doesn't have this very peculiar degenerate shell structure, still the distribution of eigenvector components is far from Gaussian. So this is shown in this plot as a gray curve. This corresponds to the 5/4 model. And we see that again, the distribution has these slowly decaying tails. Okay, so that's about, these are the main observations. We try to understand, as I said, if the peculiarities of conformal field theories are important here.
Can I point out that you have 5 minutes now?
Yes.
Right.
So as I said, there is an extensive energy level degeneracy in conformal field theories. And if we want to understand what happens at perturbative level, we find that energy levels of the same cells start mixing already at first order in perturbation theory, while they don't mix with those of the other cells. So this is what is happening when we perturb the cells. Initially, the distribution of energy density has this staircase structure because of the degeneracies. When we increase the interaction, this staircase structure gets smeared, if you want, and eventually it gets broadened extensively. And this is what happens when we look at a single cell and see and check the distribution of R tilde for varying parameters of the varying values of the mixing parameter X. So you see that even in a single cell, we still see the transition from Poisson to GOE type of statistics. I should also say that the size, the sample here, as you can see from the statistical fluctuations, is larger than those samples that we used in the main plot, the first plot that I showed, because when we restrict ourselves to a single cell, we don't have to care about convergence, because we are at the perturbative limit where lambda is close to 0, and therefore we can take as many levels as we want. So here we have several thousands of states, and the distribution is quite close to the GOE distribution, and this corresponds to the weakest perturbations at L is equal to 0.1 or 0.01. It changes very slowly at this level. This is what happens when we look at the statistics at different energy cells. So here these colors correspond to different energy cells of the conformal theory that are perturbed by the same double sine-Gordon interaction. And we see that the larger the energy of the cell, the wider the window in which this the system exhibits chaotic values in R tilde. But still, all of these in all of these cells, we see that the approach is from below the curve. And lastly, we want to see what happens if we look at different energy windows within the same cell. And we found that the distribution still doesn't change significantly, even when we move exactly to the middle part of the energy cell, where we get as close as possible to the chaotic behavior for R tilde, and the entropy of the eigenvectors is also close to the random values in the middle, and still the distribution is characterized by algebraic tails. Okay, I will leave out the discussion of error and convergence. We can have a discussion if you are interested. And with that, I will conclude. I would say that the main finding is that we studied using a numerical truncation technique a range of one-dimensional relativistic quantum field theories, and checked the spectral statistics of not only level spacings, but also the eigenvectors. And what we found is that despite the fact that level spacings are consistent with the GOE predictions, the eigenvector components are markedly different from Gaussianity and exhibit slowly decaying tails, which suggests that there would be problems with ETH and thermalization. And this is one of the questions that we would be interested in studying in the future. Thank you for your attention.
All right. Thank you for the talk.